Let me begin with a word of prayer once I get up here. Thank you for your mission too. I do appreciate it, I think. So anyway, Heavenly Father, we thank you for this day again. Thank you for these students. Just ask you to just bless our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So if you're ever sick and you can't, make it to class for turning in homework, you have several options. One is that you could send it with a friend to class. The other is you could email me a PDF of it. And then the other option would just be that I can add weight to your test, because usually I'm going to post the solution to the homework on that day, so I don't really like to take them late. Sometimes I get behind and I don't have the solution written. That's kind of a different situation, but outside of that situation, I'm trying to collect homework on time and stuff. So anyway, so there's that. So today, talking about the matrix of a linear transformation. So we're going to be thinking about, I'm going to draw a picture. So we've got a vector space V, all right? And over here, we've got a vector space W. There's some linear transformation that goes from here to there. Let's call it T, all right? And then I think we're going to be finite dimensional today. I don't believe I have any treatment of infinite matrices in these notes. So I have been in courses with professors who just start talking about infinite matrices. And I want to believe, but I just haven't. I think you could develop such things. It's just I haven't, so I'm reluctant to do that, at least in this course. But finite matrices, that we can do. So we're going to, basis beta here, we'll say V1 through Vn, n as in nanu. And over here, we'll put a basis gamma, which I'll call W1, W2, Wm, m as in mommy. And so as such, we have coordinate maps, right? We have the coordinate map under the beta basis down here to Fn, and over here we have the coordinate map under gamma to Fm. The matrix of the linear transformation is what you need to sort of complete this diagram like so. So basically just right here, we can do left multiplication excuse me, by the matrix T with respect to beta gamma. Right, left multiplication by the matrix T beta gamma works like this. So in particular, I can write a formula for it, which is that left multiplication by this T beta gamma basis is equal to, now watch this, we can do the red arrow, we can follow the diagram, all right? So I never use this orange marker, I'm gonna use it. So we want to basically do like this, all right? See that? So the last shall be first. So the last thing we do is phi gamma. And the middle thing we do is T. And then the inverse of phi beta. So you could use this to implicitly define the matrix of T with respect to the beta gamma bases like this. I will give an explicit definition, which is not this, all right? So I'm kind of getting the cart before the horse a bit, but I want to explain to you the idea of it. So that's what it does. So let's follow some points, all right? So if I start with a vector down here, let's say, x, right? Then up here, let me kind of prime the pump here a little bit easier. I'm going to call it the coordinate vector of x, okay? The coordinate vector of x down there. If I take the inverse map beta, what happens is I come up here and I've got x up here, right? So the inverse map takes the vector in v with coordinate vector x of beta back to x, all right? That's what the inverse map does. It takes the vector who has this coordinates back to that. And then, of course, you know what happens here. This brings you over to t of x, right? And then down here, we could talk about t of x sub gamma, the gamma coordinates of that. All right? So another way I could look at this is I could kind of like I think I could do it like, let's say this way, and it would be the same as this way. All right, if I start with x. So going the lower path, what I would have is L, well, let me just get straight to the point. It would give us the matrix of t with respect to beta gamma times the coordinate vector of x. All right, that's what I would get going this way. See, because I put in x, it gets me the coordinate vector of x, and then this means left multiplication by that matrix, right? So what that does is this takes x coordinate vector and it maps it to the matrix t beta gamma times that coordinate vector, like that. On the flip side, the upper path here, I just go x, I get over here to t of x, and then I calculate the gamma coordinates of it, see? This is actually a convenient way to calculate the matrix with respect to bases, beta and gamma, in an abstract vector space. I'm going to put that into practice in a calculational example shortly, okay? Like this actually is a pretty good way to figure out what this is, all right? But I guess I should actually give you the definition, and here's the definition. The definition for the matrix is just this. So here's our definition. T beta gamma is equal to the matrix. What we do is we take T, we feed it the first basis element in V, and we calculate the coordinates of that with respect to the basis in W. And then the next column, we take T of V2, and we calculate the gamma coordinates of that, and so forth and so on, until finally you get to the nth input, and you calculate the gamma coordinates of that. So that's the definition, all right? But you can prove that this definition implies these diagrams and formulas I just wrote, all right? So rather than proving that, which I'd lose all of you if I did that, right? I mean, I would completely lose you. Let's actually look at an example, and I'll try to bring this to life a little bit more. So example 1, like let's take T of the 2 by 2 matrix A, right? And let's say that's equal to A11 x squared plus A12 x plus A22. Right, so here my linear transformation T is a mapping from, let us say, R 2 by 2 to polynomials of order 2 over the R, over reals, right? Now you might wonder, is that a linear transformation? Well, it is, right? It is, in fact. And so let me just kind of draw my picture here. So I'll start with my A equal to, I guess I'll do A11, A12, A21, A22, right? And I want to figure out what's my basis for our 2 by 2, right? So you guys tell me, if I make the coordinate vector of A with respect to the beta basis just A11, A12, A21, A22, what would my basis be if I wrote that down? What would you figure out? What's my basis if I write that as the coordinate vector? What's my basis?
E11.
E11, yeah. E12, E21, E22 apparently, right? Because if I write that as a linear combination, I have weights of A11, A12, A21, A22 respective, expanding on the basis E11, E12, E21, E22. All right? And then I have my linear transformation T, so defined, right? And I got the formula up here. Here it is. A11x squared plus A12x plus A22, right? Let me call that T of A. And then I've got my gamma coordinate map down here. And I want to know what is the coordinate vector of T of A with respect to the gamma basis. Of course, I have not yet defined the gamma basis. You guys pick it. What do you want it to be? We need a basis for P2. There are two natural choices. X squared and X, what?
X squared, X, and 1.
X squared, X, and 1. In that order?
Sure.
Okay, so you're going to let gamma be X squared, X, and then 1. So the monomial basis in descending powers. Great. If we do that, what's the coordinates of T of A?
A11, A12, A22.
Great. You got it. So then here's the deal, guys. The matrix of T is whatever I need, multiply by T beta gamma to get from this 4-vector input to that 3-vector output. That's what the matrix is with respect to these bases. So what is it? You guys tell me. What is the matrix? So usually, I usually write this, guys. I usually write, okay, I want this, right? And I want this A11, A12, A21, A22. I want that vector to output A11, A12, A22, right? That's what I want. So what do I have to put here? How do I get A11 over here? What's the size of this, by the way? It's got to be a what? A 3 by 4, right? Because this is a 4 by 1 and this is a 3 by 1. So by the usual dimensionality of matrix multiplication, it forces that upon us. That also squares well with the definition I boxed over there, right? You have as many columns as the dimension of the domain and as many rows as the dimension of the codomain. So you guys tell me, what do we have here?
Would it be 1, 0, 0, 0?
Uh-huh.
0, 1, 0, 0?
Yeah.
0, 0, 0, 1?
0 apparently, right? Oh, I meant. My bad. Like that?
Yeah.
Indeed. There you go. That is the matrix. Now, of course, we could use the definition and calculate it if we wanted. We could avoid my diagram, right? You don't have to use my diagram if you don't like, but it helps me, I don't know. So like the other way to do this would have just been straight by the definition, right? So we would have had like t of what? The first thing was E11 with respect to the gamma basis, and then t of E12 with respect to the gamma basis, and then t of E21 with respect to the gamma basis, and then t of E22 with respect to the gamma basis, which would have worked out to t of E11 is x squared. So the coordinate vector of x squared, the coordinate vector of x, as it happens for this example, the coordinate vector of 1 of what's 2 1? What is 8? What is how about E21? What does that map to?
0.
That maps to 0. That's right. So that's the 0, and this would have mapped to 1. So then, by definition of the gamma coordinate map, that gives us that matrix. What do you guys think? It's good? Should we do another? Maybe? Let's see here. All right. Let's see if I've got another one. Example 2. Let's look at like T as a mapping from, let's say, P4 over R to P2 over R, where we define T f of x equals to f prime prime of x. All right. You guys know what I mean? Does it make sense? The second derivative of a quartic, is it necessarily at most quadratic? Right? Agree? Disagree? I mean, let me up the game here. Let me make this a 3, just to make it a little bit more interesting. Okay? Let me get a 3 there. So then what? So what I do is I say, okay, so basically we have, you know, ax to the 4th plus bx cubed plus cx squared plus dx plus e. That's my vector input. I'll call it v, right? So then t of v is 12ax squared plus 6bx plus 2c. Right? And if I let beta be, let me do the I guess I'll do the descending monomial basis again. X to the 4th, x cubed, x squared. Actually, you know what? Let me not do that, just to mess with you guys a bit. Let me take you out of your comfort zone. Let's do 1x, x squared, x cubed. I don't want you just to assume the coordinate vector is going to be a, b, c, d, because it doesn't have to be. All right, and we're going to let gamma be the basis. Well, I guess the same thing, 1x, but over here it only goes to third order, right? And I won't draw my pictures this time, okay? But I will kind of do this. So what we want is we want the matrix of T with respect to beta gamma times the coordinate vector of v with respect to beta. That's got to be equal to the coordinate vector of t of v with respect to gamma. See, I need to set this up for an arbitrary input to figure out what the matrix is. All right? So when I'm solving homework problems for this class, like sometimes I use this, sometimes I fall back on the definition. It just kind of depends on the mood that strikes me, right? So like either is a good method. So use which suits you more when you're actually finding the matrix. All right, so let's fill in the blank here. So what are we looking for? We're going from 5-dimensional to 4-dimensional. So we're looking for a 4x5 matrix, right? A 4x5 matrix. What's the coordinates of V? So the coordinates of V, notice I have to read this way because I put 1 as the first thing in the basis just to mess with you guys. So the coordinates this time are E, D, C, B, A, right? Because I put the first 1 is the first thing in the basis, then x squared, then x cubed, right? So as you read it left to right, you can see, well, I mean, I have to rewrite this like E times 1 plus D times x, right? Plus C times x squared plus B times x cubed plus A times x to the 4th if you want me to make the point. There, we've put the basis in order for beta, and as you can see, the weights are respectively E, D, C, B, A. And what's the coordinates of T of V? Well, we got ourselves a 2C, a 6B, and a 12A. Right? And what did I mess up? Oh yeah, and then a 0, thank you. So then what's the matrix? Zero, zero, 2, 0, 0. Okay, I agree. And then we got what? 0, 0, 6, right? And then we got ourselves 4 zeros. Wait a minute, yeah. Yeah, 4 zeros. And a 12. And then finally a row of zeros. And there you go. That is the matrix of T with respect to the beta gamma basis. And again, you could go back and, straight up calculate it from the definition, right? You could say, okay, well that's, T of the first basis is 1. Calculate the coordinate vector of that. Then you got T of x, calculate the coordinate. And would this be faster? I mean, maybe. I think sometimes that this is actually faster, but I like to emphasize the diagrammatics to try to build an intuition in you guys about like what's the meaning of it and how they interrelate. So we'll get into that shortly. See, because like the second derivative of 1 is 0. And the second derivative of x is 0. That's why the first 2 columns are 0. And then we start picking up non-zero terms. Any questions? Are we good? Yes? No? Maybe so? Yep.
Would there technically be a way to write this as a differential operator?
I mean, it is, I suppose. But the thing is, what's the domain of the second derivative operator, right? So if we think about this, if I just talk about like, d squared dx squared, what's the domain of this? See, if it's smooth functions, well, that's true, but now I am well outside the province of finite dimensional linear algebra, right? What's the basis for smooth functions? It's definitely infinite dimensional because it includes all the polynomials. It includes exponentials like e to the RT, where r is a real parameter.
You can still use polynomials because you can use Taylor's theorem.
But Taylor's theorem is that's not a span. So you've just escaped linear algebra. So yeah, we can't quite do that in that sense. But I appreciate your idea. But nevertheless, it's worse than that though. This is because there are smooth functions which are not analytic, so that won't even cover everything. This is a monstrous space, like the set of all smooth functions. It might be it might be continuum infinite. I really don't know how big this space is. I was talking to my brother on the phone, and he has a proof that the set of continuous functions has continuum dimension. So like if you look at all the set of all continuous functions, the dimension of that as a vector space is actually the same as, it's infinite dimensional, but like not countably infinite, just beyond that, continuum infinite. Like we proved for the rational functions in here. Okay, anyway, I think, so you guys feel like you can calculate these? Because I'm going to go on, talk about the structure here. So what's the point of calculating the matrix of a linear transformation? Well, here's a theorem. It's this: the kernel of T is equal to what? So let me kind of draw a picture here. Where's the kernel of T? The kernel of T, if you think about this being the origin up here, right? Kernel of T you could picture like this. Kernel of T is a subspace of V, right? How can we calculate the kernel using the matrix? See, down here, there's a null space of the matrix of T. Wouldn't it be nice if the kernel was simply what you get from mapping the null space of the matrix up here? That is exactly how it works. So it's simply the image under the inverse coordinate map, phi beta inverse, of the null space of the matrix. So I can calculate the kernel by simply calculating the null space of the matrix and bringing it back upstairs, just like that. And I can do the same thing for the image. See, the image of T you could picture as a subspace over here, right? So somewhere there's 0, right? So there's some kind of possibly, you know, the range of T, or the image of T, is a subspace of W, right? And what do you think the range or the image of T is? What's that going to be? Where's that going to come from? Like down here, right? That's 0. We've got the column space of the matrix. And it is true that if you map that column space up to here through the inverse coordinate map, that is exactly the range. What did we learn about the coordinate maps? What kind of maps are they? They're what? They're isomorphisms, right? They're bijective linear transformations. So what do those do? They preserve dimension. So you see, we can define the nullity or the rank of the linear transformation as the dimension of the kernel. The dimension of the kernel is the nullity. And that must also be equal to the dimension of the null space of the matrix. Likewise, the rank of the linear transformation can be defined as the dimension of its range, equivalently the dimension of its image, and that must be equal to the rank of the matrix. So this means I can calculate rank and nullity for a linear transformation simply by selecting any particular choice of basis I like for the linear transformation's domain and codomain, respectively. And if I can calculate the rank and the nullity with respect to that choice of bases, then I know what it is in any other choice. You're not excited? No, no one's excited. I find this very exciting, but anyway. All right, so I can tell you more here. Let me see what time it is here. I know I owe you 5 extra minutes today, but I'll try not to actually give them to you. All right, so hey, with that theorem in mind, which you could prove this theorem. It's not a hard theorem to prove, right? But I'm going to resist the urge at the moment and try to just talk more about what that means for us here, right? So like, what, as we think about example 1, what's the kernel? So as you look at this, right, it's pretty obvious that the null space is what? It's from this, right? So E3 is in the null space. On the other hand, that's it, you know? So basically the null space of, let me actually work it out here. So if I claim my theorem is what? The inverse image of under beta of the null space of that matrix up there, yeah? My claim to you is it is relatively obvious that the null space of this matrix is just E3, multiples of E3, right? It's the span of 0, 0, 1, 0. But this is an isomorphism, right? So the linear combination of anyway, you can pull a span out of isomorphisms, and so what you have is that this is the span of the inverse image under beta of E3, right? Which is the span of, let's see here. E21, yeah, thank you. In other words, it's matrices of the form 0, 0, alpha, 0, such that alpha is a real number. Now, of course, you could have easily derived this by doing what? How do you find the kernel of a linear transformation? You set the output equal to 0 and work out what that means. So if you set the formula here equal to 0, what would have happened? You know, think about that direct calculation here. If I set this, I'm not saying that this is the right way to calculate the kernel by any stretch of the imagination, guys. So, but if I set that equal to 0 to calculate the kernel directly, see that equation, equating coefficients of a monomial basis on both sides. What's the coefficient of x squared over here? Well, it's 0. So a11 equal to 0. Likewise, a12 equal to 0. a22 equal to 0. What information do we get about a21? Nothing. It's free. So the kernel is any matrix that's got 0 in those 3 components and just anything you like in the 4th. That's the kernel. But I've also seen that as a straightforward 221 calculation. I can calculate the null space of that matrix, right? Imagine the matrix is more complicated though, guys, because then this becomes more interesting, right? But even in the more complicated example, maybe it's still easier to work directly with the example. I'm not saying that this is necessarily the best way, it's just a way. What's the range? What's the image of T here? Well, that, I think you can see, is P2, right? Why? Well, we have full rank, right? We have rank 3. That's the most linearly independent columns you can have here, because we're working with 3-dimensional columns, right? You can't have more than 3 linearly independent 3 vectors, and we have them, which means that the column space is all of R3, which tracking back means that the image is all of P2R, which of course was already obvious if you just look at the formula, right? It's pretty clear that that's onto all polynomials, right? So this map is surjective, but it's not injective, right? Why is it not injective? Because its kernel is not 0. Okay? If you leave this course understanding this clearly, I have won. I'm not saying you lost. I'm just saying I have won. You also win. We can all win together. Just learn this. It's not too much. I mean, this is actually very, very simple, isn't it? It's mapping is 1-to-1 if and only if the kernel is 0. Like, know how to use that, know how to prove it. Also, I've often asked for the proof of that theorem on test. How about over here? Is this map? What do you guys think about this one? Is this one 1-to-1? Is it onto? What do we think? So this one's neither, doesn't look like it's 1-to-1, it doesn't look like it's onto either, right? So because you can pretty easily see that the null space of T, beta gamma, is the span of what? E1 and E2, right? From looking at that, I can see it. E1 and E2 multiply to give me 0, and the the dimension of the column space is 3. So, yeah. So this one's neither 1-to-1 nor onto. And again, I think you can kind of easily calculate the kernel by base. I mean, look, the right way to calculate the kernel here is not with a 4x5 matrix, is it? It's certainly not, right? What's the right way to calculate the kernel of this map? You're looking for f of x such that what? F of x in P4R such that what? Such second derivative of 0. So how do you solve that? You integrate twice. So you've got C1 plus C2x such that C1 and C2 are real numbers. How do you do that? We integrated twice. Simply that. Calculus. You know calculus. You can use calculus. Don't make it more complicated than it needs to be. So the kernel here is two-dimensional. And the basis for the kernel is 1 and x, which is in good agreement with the fact that the dimension of the null space is also two-dimensional. Right? And it's no accident that E1 and E2 map respectively to 1 and x under the coordinate maps. See, you see how this works? There's a world of matrices, there's a world of linear transformations, and the coordinate maps take you back and forth from the one world to the other. Right? I always think of the coordinate map as a machine that changes the abstract basis to the standard basis. Like, see, phi beta takes V sub j and it makes it into E sub j. And the phi gamma takes your W sub I and it makes it into E sub I. And maybe put a bar on this to show it's a different dimensions, right? This is an element of R, or rather F. I'm not keeping it real today. Fn, and this is in Fm. Conversely, if I think about the inverse map, it takes the standard basis and converts it to the abstract basis in both the domain and the codomain. So if you understand this, it can unlock many things for you. This is how the coordinate maps work. They convert the abstract basis to the standard basis, and then you extend linearly. That's all they are, extend linearly. That uniquely defines them, actually. So, all right, so let's see here. I think there's something else I'm supposed to share with you guys today, which is well, this is what I'm not remembering, is if I cover the straightening theorem before or after test 1. I feel like I had a homework problem on your quiz on it, though. So, but maybe I'm remembering things wrong, guys. Okay, yeah, problem 9 is on the straightening theorem. So, yeah, let's talk about this. So, So here's the thing. If we control the domain basis and the codomain basis, we can play a game to make the matrix work out to the identity matrix padded with zeros. Always. And the size of the identity matrix is simply the rank of the linear transformation. And the it's almost that already in this example. See it? Like if I just switch the order of the basis here, like all I have to do is swap E21 and E22, and then I've made this matrix into the 3x3 identity matrix with a column of zeros. That's what I'm talking about. Right? Over here, it takes a little bit more doing. See, what I would want to do over here is I would want to put these basis elements that are in the kernel, I would want to put them last in the basis to move all the non-zero columns over. And then if I simply divide my first basis element by 2, my second by 6, and my third by 12, then I would have the 3x3 identity padded with a row and a column of zeros. So you can see from my two examples, if you just manipulate the basis a little bit, reorder them, you can shuffle things around so that you just have the identity matrix with zeros around it. My point is that you can actually always do this. This is what I call the straightening theorem. And so let me show you that, if I can find it. So let me tell you where we're going. Like, I should probably tell you a word or two about properties of the matrix of a linear transformation. What do you think I can say about that? What do you think the linear, if I have two transformations, right, and I take their sum, what do you think the matrix of the sum is with respect to a given pair of bases? What do you guys think happens?
Probably the sum of the coordinates of the matrices of the transformation.
Right. So you think it's just we just add the respective matrices for each one? Yeah, that is exactly what happens. And similarly, like scalar multiplication, what do you think the matrix of the identity transformation is? It's the identity matrix, right? No surprise there. So like here's and the proof of these all rests on the fact that I can basically write the matrix for the transformation as a sort of like, I can connect it to the standard basis, you see, and I already know these properties for the standard basis, so then I can just rip them off from that to this if I want. I guess I did it, how did I do it here? I'm like, well, if you take phi gamma composed with this, composed with that, it's this and that. And I say that is due to the identity property, linearity properties of the coordinate mappings. But okay, so then well, yes. So let's see here. There's also a theorem if we have, a basis for if we have three vector spaces in play and we've got like a basis for, each basis for each space, and we take the composition of two linear maps, then the abstract matrices multiply in the natural way. Like the composition with gamma delta basis is you multiply the beta delta basis, beta delta matrix for S times the gamma beta matrix for T. That's the way the notation works out, like the beta being like there and there as it happens. And the proof is simply just like composition of, I have that formula over there, like that's the linear, that's the linear transformation that gives you multiplication by that matrix, and so I had that's equal to this and this. And what happens is that in the inside, the inverse map and the map cancel out to give you the identity, right? This is a map and its inverse, so they kind of cancel out. And that just leaves you S composed with T, sandwiched between the delta and the gamma inverse map. But that is exactly left multiplication by the composite matrix with respect to the gamma delta basis. So like once you understand the diagrammatics, all of these proofs become like pretty simple. This will matter to us more after test 1 when we come back and circle back and study coordinate change. I don't put coordinate change on test 1. Coordinate change is a tricky topic, so we'll come back to that later, but I'm just preparing you in part for that with these diagrams. So here's the second derivative map again, but what's the difference? Just like I made P3 the input and output, right? The domain and codomain both P3, which made us have a square matrix. But otherwise it's kind of the same example. So I have a few funny examples in here, but I wanted to. This one's kind of nice. It's really simple. If you have an invertible map, that means that the map composed with its inverse is equal to the identity, right? So if you look at that, what that means then for the matrix, right, of the identity, you get the identity. But on the other hand, if you use the theorem I just went through, you've got that the inverse transformation with respect to the gamma beta matrix bases is times the matrix with respect to the. I need to find a better name for these bases. Beta gamma. I should find like a one-syllable letter to use. All my bases have 2 syllables. It's wearing me out. So the product of those has to be equal to the identity, which means that, in short, the matrix of the inverse transformation is the inverse of the matrix of the transformation, just like you'd like. So that's kind of cool. Which also means if you're inverting a map, you can invert the matrix of the map and then lift that formula back up if you want. So here is a 2x4 example. It's not 1.5 columns and 3.5 columns. I give you full 2 and 4 columns. That's a lumberjack right there. Sorry, I'm an idiot. But anyway, the reduced rational form gives you that. So your column space is 2-dimensional and your null space is also 2-dimensional. There's its basis. And then what do I do with it? I don't know what I'm up to here. I'm up to something. I don't know what the point of that example was. I'm sorry, I wasted our time. So here is the proof of my assertions here. All right, I've written them in a slightly different way. See the difference? In this proof, I basically took the thing I wrote on the board and I took phi beta of both sides of it and phi gamma of both sides, and that's what I have up there. So it's an equivalent theorem. Let's see here. So this brings us to the rank nullity theorem, which says that the dimension of V is equal to the rank of the linear transformation plus the nullity of the transformation. And one way you can prove this is by noticing that the rank of T is equal to the rank of its matrix, the dimension of the column space that is, and the nullity of T is equal to the dimension of the null space of the matrix, so-called nullity of the matrix. Okay, but we already know for matrices that the dimension of the column space plus the dimension of the null space must be the number of columns in the matrix, right? Because column space is spanned by the pivot columns and the null space is spanned by the non-pivot columns, and either columns a pivot or a non-pivot, so the sum of the columns, the number of those, must be the number of the null space dimension plus the number of the column space dimension. So because of this transference of the coordinates, we also have the same for the rank and the nullity of a linear transformation. And, oh man, where'd that go into? So we're going to talk about dual space next time. So my apologies, I seem to have given you a homework problem about material after test 1. So, tell you what, I'll make it up to you. Problem 9, you may omit. There we go, fixed. Extra credit. No, it'll come back. It'll come back. You can cross out problem 9 for now, yeah. That is, after all, after the section that, like the next section, section 3.5 is the last section I covered before your test, so, I'm sorry, I try to fix everything